Hi, everyone. Do you hear me clearly?
Hello.
Hi. Yes, we can hear you
Great.
clearly.
Okay, good. So I wrote in the chat that we will have a little test in the beginning. So you can have your time and pass all the answers there. And then we will discuss it, why correct answers are like, okay, which are correct answers and why. So this short test to help warm up your minds, and you can take a few minutes to answer all of these questions.
Sorry, have you already shared the link to the questionnaire?
Okay, I shared it in the Telegram chat, so I can double it here. 1 second.
Yes, please. Thank you.
Do you see it?
Yes, thanks. I can see it. But do you have a separate group, like for NLP course? Maybe I'm not part of that group.
So you're talking that you have you can see the test?
No, I mean that you mentioned that you already shared this link in the Telegram chat.
In the Telegram chat. Yeah, I can share your link of the Telegram chat too. So I thought that everyone is there already. 1 second.
Awesome. Maybe I missed that. So thanks for sharing.
Okay, I recognize that I can't copy the link, invite link to the chat. I will tell my colleagues that I need this link, and later I will send it when I will receive it.
Thanks a lot.
I can share the link with you in the chat. So it is now there. Okay, will we have only 2 people on the lesson, or maybe we will wait for more people? bad tendency. In the beginning, we had more people than now. Okay, so I think that nobody will let in. Do you need more time for the test, or shall we begin?
I am done with the test.
Vladimir, what about you?
Yeah, I need a couple minutes more. I just started a bit late.
Okay, no problem. No problems. Okay, so I will share the screen. Now I think we can see the screen, and we will put this we can discuss all the questions and we will discuss theoretical information about all of this stuff that you had in the quiz. So let's get started. The first question is about batch normalization words. So the correct answers is the first one and the last one. Why? During training, batch normalization uses the statistics from the current batch. However, during inference time, it requires previously computed mean and STD values. The mean and STD values are computed independently for each feature across the batch, but not overall all neurons in the lower. So do you have questions here, or we will move to the second one? One, two, three. Okay, I think we have no questions. Okay, here correct answers first one and the last one, because back of words assumes that each word in the document is independent of the others, and the other order of the words doesn't matter. So the model only cares about word frequency, not their order, which can be a limitation for more complex language models. So because of this, first one and the last one. Okay, 1, 2, 3, word to vec. Here correct answers first one and third one, because word to vec is a neural embedding method, and that represents words in a low-dimensional space and captures the semantic meaning based on their context. It doesn't require labeled data like, for example, WordNet, and it learns from large corpora through the context that we have in the text. Here, the right answer is the middle one, unlabeled to work with unseen data. Because it needs a large corpus of the text to learn word embeddings. However, once trained, it's capable of working with unseen data using the trained vectors, and it can incorrect new words through retrain of or fine-tuning. Okay, we have a question. How about option 2? Where option 2? Needs large number of text to train on. Okay. Needs large number of text to train on. Okay. Yeah, maybe it's it makes sense. Yeah, but okay, I think we can answer like this too, like a second one and third one. No, okay, we discussed, so I said that we can, okay, I just mixed up options that we have there. So yes, of course, it's only this answer. Sorry about this. Okay, it was is unable to work with unseen data is wrong answer. No. One second. Is unable to work with unseen data. So word2vec works with the context. So if it so in the context information about all of these words that we had, it can work with it. But if we hadn't this word in the vocabulary, we could not also we can't recognize meaning of this word. In this case, if we hadn't word in the context in our corpora, we can't can't know its meaning. Is it clear?
I have a question about this case. If we have a word which we don't know the meaning, how about because it's in between a sentence and we have a context, is it possible to infer the meaning of this word?
Yeah, word2vec work on the frequencies. So we can work only with frequency of the context.
Yeah, but I mean, if we don't know the meaning of the word and it's not in our training data set, then we would be able to understand, I mean, approximate this word, right?
Yeah.
So the true answer is only 2, option 2, need larger number of text.
Let me think. I think we can. I sure that okay. I think number 2 is almost the right question. What about third one? Some label to work with unseen data. You said okay, your opinion is right in that case, that we can try to understand meaning of the word with its context information, and it's right way of thinking. But I'm not sure that in formalization of this task, it would be almost right question, right answer. It's this test not influence on your mark of the all the course. So I think if you worry about like right answers, it's okay to just have right way of thinking, and that's it. But okay, I just not sure to say it. Can we say that this answer almost right of the formulation?
Actually, I searched for it right now, and it says that it is impossible to work with out of vocabulary, let's call it, words. And if there is a word which is not inside the training corpus, it is a limitation of this model to inference on those part of text that we don't know about. So it requires.
Okay. Okay. So okay, let's move to the last question, and here's right questions is middle one and the third one, because Word2Vec works on district objects, which are the words in the vocabulary, and the frequencies of the words are imbalanced because certain words appear far more frequently than others, which can affect the learning process. And techniques like some sampling are used to deal with this issue. Okay, if we discussed all of the theoretical information, we can move to the code. We will have interesting seminar today, I think, because we will cover a lot of information. We'll discuss not only back of words, Word2Vec, techniques in natural language processing. We will almost cover your map. It's imported here, and there would be a PCA method. I promise that it will be a lot of fun today. At the first step, we will just load all of libraries that we have here. And the second step is to load dataset with which we will work today. It's consists of the questions. The file is plain text format, and our first step will be load this data and prepare it for processing. So I loaded yesterday, and because of this, I have these files here. So I can just run third step of our code. We load this data into a Python list and take a look at a sample and try. This will help us understand the format and how we need to clean it up. Here we see a sentence that we have in the data set. And next we load, okay, we loaded our formation. Here's an example of one of the lines. Now it says in a raw format, so we need to clean it and tokenize it. We will do it here. In natural language processing, tokenization is one of the first steps. It involves splitting raw text into individual words or tokens. However, because of punctuation and special characters, using a simple, for example, stir point split won't work. Instead, we will use the NLTK here library, which has specific tools for tokenization. You can see here that we tokenized text split into to the words. Now let's take it a step further. I want you to lowercase all the text and apply tokenizer to each line in data. Your task is to create here. Okay, it was your task to create line of code, but we had now code here, so it's list of lists where each list represent a tokenized version of one line from the data set. We can check it here. Let's check if the data is processed correctly by making sure every line is converted into a list of strings. We can run asserts. Okay, we see that everything is working in the right way. Next, let's make sure everything is lowercase. Since we are working with English text, we'll define a function to check if all tokens are in lowercase. And it is then we have word embeddings. We have tokenized our data. We can move on to word embeddings. Word embeddings are a way to represent words in a continuous vector space where semantically similar words are close to each other. There are many methods for creating word embeddings. One of these are word2vec. Also, we have glove method, and fast text is 3 similar ways to create embeddings of the text. Let's start with word2vec using Genzim library. Okay, now we can get vectors for individual words. For individual words, for example, we have cat word. We can get its vector. 1 second, and it will be it runs. Okay, so we have vector for cat word, and also you can query the model for words that are similar to another word. Let's find the similar word to red, and we see that it print most similar words for the red example. We have poem, bleach, and others. Okay. Now we have further API method. Why do we have it here? Because training word embeddings from scratch can take a lot of time and resources, especially when working with large data sets like Wikipedia or Twitter or maybe Reddit, I don't know. Likely we have pre-trained models available, and we can load one of those using Genzim downloader. We see it here. So we did it. and we can check that it works. And it is. Okay, let's go further. One way to access the quality of your word embeddings is through visualization. Since our word vectors are in high dimensional space, we need to reduce their dimensions to something we can visualize, and we can plot the 1000 most frequency words using dimensional techniques like PCA or TSNE. So we can just do it here. And then we will depth to PCA method. Do you know what is PCA method? Did you method earlier?
Yes, it's a principal component analysis.
Mm-hmm.
So basically, yeah, we try to instead of one matrix, we try to create 3 matrices. Or is it?
Mm-hmm.
Yeah.
Yeah. So I will just reformulate the meaning. So it's a technique you use to reduce the dimensionality of data while retaining most of its variance. It does this by projecting the data onto a set of new axes called principal components that capture the direction of maximum variance. In simpler terms, PCA finds the most informative directions in the data and projects everything onto those directions, reducing the complexity of data. So why we are using this? We're dealing with high dimensional word vectors, but visualization such vectors is difficult for us, and PCA allows us to reduce the dimensionality of two-dimensional so that we can visualize the vectors and understand their structure. We can do it step by step. So we in the first line import PCA from sklearn library, which provides a simple way to perform the decomposition. And we also download standard scaler. Scaling data before applying PCI is crucial because PCA is sensitive to the relative scaling of all of the features. And standard scaler ensures that each feature has a mean of 0 and a variance of 1. So here in these 2 lines of code, we initialize PCA with 2 components, meaning we want to project our data down to 2 dimensions. That the result will be 2 principal components that capture most of the variance. And in this line of code, this object will be used to standardize our data after PCA to ensure the vectors are zero-centered and have unit variance. So then here we applies here we applies PCA to the word vectors. It finds the principal component and then project the word vector onto those new assets. And further, after applying PCA, we scale the results. So it's here. So the new vectors have 0 mean and unit variance. This normalization helps in visualization and compression. So we can run it. We can run asserts, and now we can just draw it. Okay. After applying PCA, we can visualize two-dimensional word embeddings to understand if words with similar meaning cluster together. This will help us verify whether our embeddings capture semantic relationships between the words. Okay, we need to just download it. So we use this library. Oh, okay, it's okay. For interactive plotting, and this allows us to render plot directly to the Jupyter notebook. Let's wait for the result. We have while we are waiting, I will explain what we have in the code here. The draw vector function plots data points in two-dimensional space. The hover feature is practically useful for interactive exploration, allowing us to see which word corresponds to each point. We have here this method, and it holds the data to be plotted. We have X value, Y value, and color. And hover tool here enables the tooltip features, so you can hover our points and see associated words. It's downloading. And here we have clothes. This draw plot the words vectors after PCA, and you can now hover over the points and observe clusters that we have. Okay, you can just put here the cursor and just see around which words do you have. Here we have UMap. Unlike PCA, which is linear, UMap is non-linear dimensionality reduction technique. UMap tries to preserve the local structure of the data, meaning that points that are neighbors in high-dimensional space should stay close to reduce space. While we're using it, it's better at capturing local relations and clusters in high-dimensional data, which makes it's a good tool for embedding visualization. And when you are working with complex structures like word vectors, you can use it. So earlier we imported UMap, and now we can use it. We can use UMap. Here this is number of parameters controls how many neighboring points each point should consider. during the embedding. The choice of this value can influence the structure of resulting plot, and fit transform, like PCA method, reduces the word vectors to two-dimensional for visualization. So it's running in the code. Here we use it to this uses the sample plotting function as before to display reduced vectors using UMAP. And here we have another plot. We can notice the difference between these two methods. While PCA captures global structure, the main directions of variance, UMAP focuses more on local structures. So you often see cluster form more clearly. And you can recognize it here. Okay, if we will move on, we have then phrase embeddings here. Yeah, words are great, but we often work with phrases in real world natural language processing tasks. So to create a phrase embedding, we can simply take the average of the words embeddings in that phrase. This gives us summary vector for the entire phrase. Here we have it. So we have tokenization here. The phrase is tokenized into individual words using this tokenize method. And for each token, we retrieve its embedding and compute the average. If the phrase contains no known tokens, we return 0 vectors. And we can see it okay, in the averaging. We can see it here. So let's run the code. Do you understand why we are averaging the embeddings? Okay, I think no.
No, could you please share more?
Okay. By averaging the embeddings, we capture the gist of the phrase, assuming each word contributes equally to its meaning. Okay, we can see all of the stuff here. We just do it in all of these lines of code. And then we build an asymmetry engine. We can now use our phrase embedding to find similar questions in our dataset. Given a query, we will compute the cosine similarity between the query embedding and the embeddings of all other phrases. We can see it here. So cosine similarity, this measures the angle between two vectors, and cosine value of 1 means the vector are idental, while 0 means that are orthogonal, yeah, and completely dissimilar. So, and arc sort here sorts the distances from most similar to least similar, and returns the top k results. What's going on here? Okay, it's run. Okay, so we see here how it works. We ran all the code that was here. So then we use convince method. This method clustering to group similar phrases together. This help us discover patterns of topics in the data. This algorithm groups data into n clusters. Here is like, I think it's yeah. Here we have 3 clusters. We set to 3 to divide the phrase embedding into 3 groups. And when we can see now that here we set colors for the clusters, and each cluster gets a different color for easier visualization. We can see it here. Yeah, so I think it's clearly here to recognize that we have clusters here. So maybe now you have some questions why we do this, and also here you have short notes what to do next to understand it better. You can try to quote by yourself other methods. For example, this and instead you map and see how it would work. What will be different with previous method.
So basically, we have 3 like different clusters there, and it's based on the same words or the same meaning of the words. What is that on the picture?
Yeah, it's so we recognized we visualized that we have clusters of phrase embeddings. It has different meanings, and we can visualize it in the on the plots. Usually, when we work with real projects, on this step we can visualize all our features, how it's connection with each other, and so it's called the EDA step while we see how our data is connect with each other, and visualize it in different ways. So yeah, you're right.
Okay, thank you.
Maybe you have more questions on this step. Okay, if not, we have the last task here. It would be short, but we will write code together right now. So as on the previous lesson, we can do it together. And I recommend you to have a double screen or second screen right now, because I think it would be better if you will write with me code, and maybe you will maybe if you will write it first before me, you then can check do you think in the right way, or maybe we will discuss some different issues for the process, and so I think it will be better. Okay, I will just start to explain all the tasks that we have here. But you can start to try to type code in these sections where you have comments with your code here. Okay, let's go step by step and fill the missing pieces of this code. We start by defining the vocabulary and the mappings between words and the indexes. This is crucial because our model needs to convert words into numerical indexes for training. So we have word to index and index to word. I will fill the gap by myself, and then I will explain what I did. Okay, word to index, this is dictionary that maps each word in the vocabulary to unique integer index. We need this because neural networks operate to numerical inputs, not words. And also index to words, it is the reserve mapping that converts an index back to the each word. So we can just run it. Okay. Okay. Now we need to create pairs of target words and their context words, as word is trained by predicting the context of a word, of predicting a word given its context. Like there are two ways how we can train it. Here, what is W equal 4? This is the window size. It means we are looking at 4 words before and 4 words after the target word as a context. Yeah, and what is crucial here? onto the tuple list, I think here we built a list of target context word pairs where each word in a sentence have several words in its context. For example, I don't know. Okay, did you understand what I said? So just list for target and context word pairs. And so here in this code window, we have xtorch. This contains the indexes of the target words, and here ytorch contains indexes of the context words. Why we have long tensors? Maybe you will try to understand by yourself why it is long tensor here, or I can explain first.
Can you explain, please?
Okay, we use long tensor because the inputs consist of integer indexes corresponding to words. So in this case, we use this format. And for the fourth step, we can define the word to Vec model. Okay, yeah, we need we need type the code here. Okay, let's define a neural network model. This model will learn to map words represented as indexes to dense vectors embeddings. So I will now type the code here. But this is here. Okay, so here we have embedding layer. It maps each word by its index to dense vector. This is what the model will learn. And here we have linear layer. It's fully connected layer. It takes the embedding and outputs as predictions for the context word. Okay, also we have forward method and it defines how the model transforms the input with first get the embeddings and then use the linear layer to predict the context words. Is it clear?
Yeah.
Okay, so yeah, I have a GPU here. Then we define cross entropy. What's it? Reduce the linear output. Where should we import it? We just will use this one. Okay, so cross entropy loss, because we use frequencies, we use this loss. It's a loss function. It's commonly used for classification tasks. Here we are trying to classify which word of our entire vocabulary is the most likely context. Because of this, we use this loss function. Also, we here use Adam optimizer. This optimizer adjusts the weights of the model based on the gradients of the loss function. And we have linear rate scheduler, not linear, sorry, just learning rate scheduler. Reduces the learning rate when the loss plots places to help fine-tune the model. And
What is patience parameter?
sorry?
There is reduce LR. What is patience parameter?
Can just hear.
Okay.
And just yeah. So read the documentation because I don't have it in the cache of my mind. So yes,
Okay.
a number of loft epochs. So what is going on here? Embedding. Sorry, yeah. I just that embedding. Embedding. Done. Okay. So we are ready to perform the actual training. We'll use stochastic gradient descent, updating the model with small batches of data at a time. It's training loop here. So what do we need to type here? We have X batch, Y batch. But we need output. Well, we will pass X batch, and also we need loss. Well, we will pass output and our target samples. Also, then we need 0 grad. And then backward. And then step. So it's base train loop. We didn't do anything what we didn't know on previous lesson, on maybe on previous courses. X batch and Y batch is random mini batches of the target and context pairs. Forward pass is when our model makes predictions based on the target works. Backpropagation is when the loss is computed and then used to adjust the weights of the model through backpropagation. And learning rate scheduler adjusts the learning rate if the loss stops decreasing after some time. Now we can see a plot of our loss. I think it's a good way of. Okay, we didn't do something wrong because I just fall through all training loop. So finally, after the model has been trained, we can access the learned word embeddings and find similar words. What we have here? Because I drop S. Oh, sorry. So, what we have here, constant similarity, when we measure how similar two words embeddings are based on the angle between these vectors. The closer the angle is to 0, the more similar the vectors are. And get closest, this function returns the top n most similar words to given word based on the learned embeddings. Here we can see how it works. Apple is close to all of these words. So this is the end of task. What was difficult for you? Maybe you have questions right now.
So
No question?
basically, so the understanding, so the function gave us the closest to the word apple by the meaning, and this is what we got, right?
Yeah.
Okay.
No,
Including itself.
we can see that algorithm works. We have similar words, like we learned all information through train corpora, and we learned text like linguist similarities of our text. How does it name in the right way, like okay, and just text linguistic connections. I don't know.
Okay. Yeah, and it says that it might look not promising. So basically, there's a way to improve our function.
Mm-hmm.
Okay. Yeah, because it like the closest itself, and the other words don't make apart from tangles don't make sense. Okay.
Yeah, because of this, right now it's not a state-of-the-art method. So if you're interested in right now in this task, when we need to get embeddings and to have similarity from the text, we use transformer models. We will learn it on the fifth, I think, lesson. And so we just create embeddings with transformer model, and then we can search the nearest embeddings around our word. In this case, we will not have a lot of problems like we had in such algorithms.
Okay, thank you.
Mm-hmm. There was one more question, I think.
No, it was just a quick comment that it's okay. I mean, the embedding that we see here just make no sense, but you already provided the comment, right? So because it's not kind of an appropriate modern method.
Yeah, it happens sometimes, and I didn't see that now somebody use it on their projects. Sometimes engineers use TF-IDF method. I'm not sure that you had it in the lecture. Let me. Did you have?
I think we did touch on the TF-IDF, which is tone frequency, interdocument frequency, I think.
Yeah, and sometimes natural language engineers use it because okay, it's not state-of-the-art method, and we have embeddings from transformer, but sometimes we don't need context of all our texts. Sometimes it appears on, for example, projects in banks when engineers have haven't good context. It's not clear or doesn't consist with each other. And in this case, sometimes engineers say that TF-IDF still works and they use it.
What about if, for example, if you have a problem from very general corpus domain, like maybe news article, right? Would you in English, let's say, right? Would you train a TF-IDF embeddings, or would you take existing one of existing models that are already pre-trained?
If I have problems in my own model, or I didn't recognize the meaning of the question.
Yeah, I mean, just the general meaning of the problem. Let's say just the corpus from the very general news articles, right? So without specific domain of knowledge. So
Yeah,
this is just the news, right? That you're dealing with.
yeah, I got it. Yeah, right now in the real projects, nobody use model which pre-trained like from the scratch. We use already pre-trained models and then fine-tune it on our specific task. Because of this, we solve these moments. Usually, we have big pre-trained models. For example, okay, if we discuss embeddings model, we have around 300 millions of parameters. And we already passed a lot of text in this model. I talk about trillions of tokens. So in this case, our model know a lot about real world, and we have no issues to train it on our specific domain. It will learn all of stuff that we have in text. But if we have not clear, we haven't clear corpora on our works, for example, in this case, sometimes pre-trained models doesn't work well. And in this case, engineers use TF-IDF method, and it helps. But to answer like to answer it, this question haven't right answer. You need to try all of hypotheses that you have, and for example, calculate your own metric that you optimize in your work. And or after your experiments, you can say for sure that one of your hypotheses was good.
Okay, thank you.
Maybe more questions? If we will not have questions, we can stop our lesson earlier.
No question. Thank you.
Okay. Thank you so much for your attention. It was interesting to talk to you today.
Thank you.
Okay, see you next week. Goodbye, guys. If there would be some important information, I will send it in our chat in Telegram.
Can you tell when will we have our first homework?
Our first what?
Homework.
Homework. Yeah, so today I will receive information about dates of your homework. Your first homework will contains of embeddings learned today. So I think I will know it today, and I will text it in the chat, because I'm not sure now. Maybe I will send it on this week, maybe on next week. I don't know.
Okay, thank you.
Thank you so much.
Goodbye.
Goodbye.